Class, today we're going to talk about lesson 5, which is continuity, and which corresponding to section 2.5 of your textbook. Before coming to this class, I hope you already reviewed the handout I posted, which is the graph for some basic function that we frequently encounter in calculus, and also the handout on the function dense. So I hope you're familiar with the dense move for those basic functions. All right, so let's get started. So before this lesson, I hope you already print out the note on Canvas, this 2.5 lesson note on Canvas. So you can fill this out as you watch this video. Okay. So 2.5 continuity. Okay. Well, how is it defined? Okay. The definition for continuity is a function is continuous at a number a if the limit of this function as x approaching to a is equal to f of a, which means you can do a direct substitution of this a into this x right here to find this limit. So that's just equal to f of a. Okay. So now some of you might feel that it's a little bit hard to visualize it. Basically, if you're looking at the graph of a function that's continuous at a, it just means that the graph has no gap over here. So you can go from one side of this graph to the other side without lifting your pen. So this is a formal definition for a function f that's continuous at the number a. So you can do direct substitution. And if you try to visualize it, then the graph will have no break at a. Now, this definition over here, the function is continuous at a if the limit of f of x as x approaching to a is equal to f of a. This definition actually requires three things. Okay, number one, it's required that this f of a is defined. Okay, defined means it's defined as a real number. Number two, the limit of this f of x over here had to exist as a real number. Number three, the limit of f of x as x approaching a has to equal f of a. So number one, f of a had to exist. Number two, this limit has to exist. Number three, they have to equal. Okay. The definition says that function f is continuous at this a over here. If f of x is going to approach to f of a as x approaching to a. So a small change in x over here produce a small change in f of x over here. In fact, the change in f of x can be made as small as we want by keeping the change in x sufficiently small. Okay. Now, if the function is not continuous at a, we call that as discontinuous at a. Okay. So there are three cases the function is not continuous at a. Okay. So number one, f of x is not defined at a. Okay, so maybe I should put it down here. At a, defined at a. Okay. Now let me give you some example. This example over here, this function is not continuous at this a because the function is not defined at a. When x equal to a, this is a gap right here. The function is not defined at a. So there is a discontinuity at a. This discontinuity here is a removable discontinuity because you can move from one side of this graph to the other side of this graph by simply just fill in this single dot over here. Then we can go from one side to the other side. So this is a removable discontinuity. Okay, this second example here, the function is not defined at a. So you see there's a discontinuous at a. The function that has a discontinuous at a. You can there's a break over here. Okay, you cannot go from one side to the other side by filling in just a single dot right here. So this is a non-removable discontinuity over here. You cannot just remove the discontinuity by filling in a single dot. Okay, so non-removable. This is removable because you can put a dot there to move from one side to the other side of the graph. Another case that the function is not continuous at a is the limit does not exist at a. Now let me give you one example. Now this example over here, you see that this is the same example here. The limit as x approaching a does not exist. Okay, it's not the limit as x approaching a is not a real number, so the limit does not exist. Okay, so it has an infinite limit, infinity, but infinity is not a real number, so that's a special case of does not exist. Now this is what we call an infinite discontinuity because the limit here goes to infinity, so that's an infinite discontinuity here. It's also a non-removable discontinuity. You cannot remove the discontinuity by filling in a single dot. This one over here, this example, we have a jump discontinuity here at A. Okay. So at A, so we certainly jump from here to here. So this is a jump discontinuity. Is this a removable or non-removable discontinuity? Well, if I fill in a single dot, I cannot go from one side to the other side. So this is a non-removable discontinuity. Both this one and this one are non-removable discontinuity. This third case here, the limit exists and f of a also exists, but they don't equal each other. Then we have a discontinuity at a. So take a look at this example. You see this function over here is defined at a. F of a is defined to be this value over here. The limit as x approaching a from both sides also exists and equal to whatever this number over here is. Okay, let's call this number. Yeah. Okay. So, however, this limit and f of a are not equal. So this function is not continuous at this a. So you can see on the graph there is a break over here. This is a removable discontinuity because you can fill in the single dot here to go from one side to the other side of the graph.